All right, let's get started. Let me do that. Okay, so just a few quick housekeeping items. First off, just don't forget that class is canceled next Wednesday. In terms of content today, what we're going to do is we're going to finish out probably seismic loads today because we have an example we're going to do. We're going to look at gravity load effects very briefly for, in case there's a couple people in here aren't in concrete design, just to make sure everybody's on the same page. Get up to speed with some LRFD load combos. If you've already had concrete design, you've seen this stuff. And then that'll pretty much be it for today. Once we come back next Friday, we start into steel design land. Now, I'll say this, probably, next Friday, it's not desperately necessary that you bring your manual, but after that, you're probably going to start noticing that you kind of need it. So I would just plan to have it with you, at least like starting week 3, just have it with you from here on out, because we're going to make a lot of references to it. A lot of the examples that we do in class, I'm going to need you to be, looking at data and values from the manual. So you will just need it. I know it's bulky and I know it's kind of big, but starting then you'll definitely need it. As for homework, I do have a homework for you today. This one is pretty short. It's a 2-problem assignment on lateral loads. I'm giving you a frame, a single frame, and having you do wind and earthquake analysis on it, and then I'm having you use the hazard tool to just look up some base wind speeds and some accelerations. Pretty simple stuff. I imagine this homework will be very, very, very fast. Any questions? All right. So. Okay, so last time, let me see if I can go back. I think that's a good place to start. Okay, so last time, if you recall, and just to sort of recap what we've been talking about throughout the week, we started off with trying to just define from a 30,000-foot view what it is that we as structural engineers are responsible for in a given project, and just trying to look at things holistically. And then in this course, we spent the remainder of the time looking at lateral loads. Between gravity loads in concrete design and lateral loads in steel design, it gives you sort of a complete picture of what's going on. So last time, we spent a good bit of time looking at wind. We did a pretty comprehensive wind example looking at computing pressures. I think you found that was it's a pretty straightforward calculation. We talked about some additional issues that you can experience with wind, things like negative and positive internal pressure, things like accidental torsion, and what have you. So I think you found that's pretty straightforward. And so we started talking a little bit last time about seismic, about earthquakes. So again, really where you get your earthquake loads and where you get your forces that you apply for structural analysis comes from F equals ma, force equals mass times acceleration. The building obviously has a mass to it. It's not light as a feather. It has some significant weight. And when an earthquake strikes, what it's doing is it's taking that building and moving it through an acceleration. Now, the ground is going like this, and it's causing the building to accelerate. And so force equals mass times acceleration, in general, will tell you how much force is being applied to the building. Now, it's a little bit more complicated than that, obviously, because there's a lot of math you got to do to get to those forces, and that's, I think we're going to kind of try and get there today. So the general process for determining seismic loads on a building is, first off, you got to determine your response spectrum, which is characteristic, basically your ground characteristics at the location. So that's going to change. We're going to have a different response spectrum here in Huntington than you would in, say, Los Angeles. And we actually looked up response spectrum last time. I'm not going to do it again, but I'll show you some basic spectrums here in a second. Then you got to determine the building's period of vibration. I'll recap that here in a second. And then determine the response coefficient. That response coefficient, that C sub S, basically tells you how many G's the building is subjected to. So the building has a certain weight, let's say the building, just make up a number, say the building weighs 1,000 kips, If it's going to be subjected to 0.2 Gs, then that means your total seismic load would be 200, 200 kips. And so we call that the base shear because here's the building and the earthquake is moving like this, so it's sort of like it's shearing the building. And then the only thing you have left to determine is, well, how much of that shear would get applied to each story? How much goes to the first story? How much goes to the second story, et cetera? And then you can break out RISA or whatever software package you want, or if it's determinate, do it by hand and do your structural analysis. That's pretty much it. Like I said, your ground response spectrum is dependent upon where you're at in the country. You can get a different response spectrum, obviously, here in West Virginia than you would in, say, San Diego. Obviously, that's going to change. So if you recall, last time we looked at using an online tool to determine what would be the response spectrum for a typical office building in Huntington, West Virginia, if it was of risk category 2 and a stiff soil was found at the site. And so we went through that, and we ultimately derived response spectra that looked kind of like this. So I don't have the one for Huntington pulled up, but I do have the one for New York, and for LA. Now, obviously, if you're designing a structure in Los Angeles, you're going to have larger ground accelerations than you are in New York, and that's represented in the graphs. You can look here. Just look at your y-axis. So you're having some pretty high accelerations over here on the right, as opposed to what you have here on the left. Now, that's great and everything, but what it's not, or what probably doesn't make a lot of sense right now, or okay, that's great, Dr. Mike, but how do I use this? Is you kind of need to know what's going on with this x-axis, what's going on with the period. So what is the period of a building? Well, basically, it's how long it takes for that building to undergo one cycle of vibration. Remember, we use the instance of a guitar string or a bass string or any sort of really any element. You take that structure. I used the guitar string last time. If you were to play a guitar string, once you let the string go, the string obviously vibrates. It vibrates at its natural frequency, which is why whether or not you play a string very lightly or you really wail on it, you get the same note. You get the same tone that comes from that string. And that's because while you're getting a different amplitude at whether you play it lightly or really wail on it, it is still vibrating at the same frequency. And so that natural frequency is a very fundamental computation that we need to be able to perform in structural dynamics. And to be fair, that computation is kind of difficult, especially if you're trying to consider damping, if you have a structure with a lot of degrees of freedom. That's a very difficult task. I mean, there's a whole subdiscipline in structural engineering called structural dynamics, trying to characterize the dynamics of a vibrating system. Fortunately, the code realizes this. It seems that, you start talking about fourth order differential equations and all this crazy math, and engineers who love math, when you start bringing that stuff up, they're like, I don't want to do that. Fortunately, the spec gives you a means of computing approximate periods of vibration, so it's pretty straightforward. All you need are three things. Two of them are constants depending upon the type of frame that you're looking at. So whether or not you're looking at a braced frame or a moment frame, I think it would stand to reason that braced frames versus moment frames are going to vibrate differently. They're going to respond differently and have different natural frequencies. So all you need are the type of frame that you're looking at and those associated constants and the height of the building. So the taller the building, the different, with changes in the height of your building, you get a different period. And that's basically it in a nutshell. I'm a popular guy, I guess. And that's basically it. Don't worry, we're going to go through an example looking at this. Any questions so far?
So just like before you talked about the car string,
yeah, but theoretically, yes, but in practice, that's not really how we would go about changing the frequency in a building. That's not to say that changing the frequency in a building is not something that we desire because it very well is. How many of you have heard of the Taipei 101? It's a building in Taiwan that has a tuned mass damper at the top of the building. Basically a big old hunk of concrete at the top of the building. There's a reason for that. Not just a building, but a structure in general, its vibration characteristics are really a function of three things. It's a function of the system's stiffness, it's a function of the system's mass, and a function of the system's damping characteristics. Now, damping characteristics, that's probably the one that's the hardest to quantify, but if you can change a building's damping characteristics or change its mass characteristics, you can change its frequency. So that same guitar string that we're talking about, another way of affecting how that guitar string played would be to make it heavier. Even if it was under the same tension. If it was a heavier string, it would play differently. You know, same length, same tension, but make it heavier, different frequency. So, but you didn't know that. So, you learned something. But yeah, in what you're saying though, like could you take the structure and make it tight, tighten the structure? I mean, I see what you're saying, but in practicality, achieving that would be very difficult and difficult in a reliable, predictable sense. Usually what you're trying to do when you're changing the damping characteristics of a structure is you're trying to install elements to do that. So tuned mass dampers, there are base isolation techniques where you sort of like sit the building on some elastomeric rubber pads that sort of change how the accelerations get distributed to the building. There's a couple of different ways to do it. There's a boatload of different ways to do it. But that's, man, I could talk about that all day. Any other questions though? This is good stuff. All right. So keep in mind, we're ultimately taking the building's period of vibration and that response spectrum in order to determine how many G's are on the building. Actually getting to that point it takes a little bit of discussion, and I'm sort of glossing over that, but there's a lot that goes into that. The importance of the structure, remember the risk categories. Risk categories play an important factor, so whether or not you were designing for risk category 2 or risk category 4, that's going to change how this goes about. A real big one, and this one takes a lot of like theoretical discussion, and we'll kind of touch on this later when we look at yield strengths, but how much yielding is tolerated in a structure changes the accelerations that you're willing to accept. And I want to sort of gloss over that for now, because when we start talking about yield strengths later, I think it'll be a little bit easier to understand. But also the location and the period. So what I'm sort of interested in is your ability to do this. So let's say I give you the building, and I tell you how many G's the building is responsible for. Can you determine the force that is meant to be applied on each story? And so basically what we're doing when we do this is we have, let's say, a total base shear of 500 kips. How much goes to each story? And so I want to teach you how to perform that seismic load distribution. It's actually really not that difficult. All you need is the weight of each floor, the height, the story height, and then this distribution coefficient. And this distribution coefficient is a function of the period. And so if you have a building period that's less than 1 second, so it would undergo a cycle of vibration in 1 second, use a K value of 1. If it's a value greater than 2.5, use a K value of 2, and anywhere in between, just linearly interpolate. So with that, I think what I kind of want to do is stop talking and start doing. So what I want to do is I want to go back to that same building that I was looking at, and I want to look at this from a seismic perspective. So I have here that same frame. This is the same frame from example 1A, and let's say, I'm going to try and fold this down. Let's say that that frame has the following weights. Now when you're looking at seismic analysis, you typically, what you do is you compute the weight of each story and sort of lump that as a single load. Because think, as you're starting at the ground and sort of working your way up, really the heavy parts of the building are the floors, the individual floors. So like right here, remember our secret weapon of structural engineering, right? Remember the samurai sword or the lightsaber if you happen to be a sci-fi fan? If we cut through the building right here, like right here, we would be cutting through a lot of air. Like we'd cut through the walls, but there's a lot of air right here. Whereas if we cut through the building right here, that's a lot of slab and a lot of beams and a lot of elements, right? So really, where is the building's weight concentrated? It's concentrated at each story. Like you have some columns and then a bunch of weight. Some columns and a bunch of weight. Some columns and a bunch of weight. So does it make sense? When you're analyzing a building, it sort of does make sense for you to assume that it's a bunch of lumped masses at each story. Make sense? So I propose that for this building, the second story weighs 250 kips. The third story weighs 300 kips, the fourth story weighs 200 kips, and then the roof weighs 50 kips. What I want to do is, if I have a seismic response coefficient of 0.1, I want to determine what are the seismic forces that I would apply to this building for the purposes of analysis. And that's sort of what I want to try and determine here. So, let me move this. Give me a sec. All right. There we go. Now, I'm going to screen capture this frame because I'm a little lazy. There we go. Everybody read that? I'm going to move that over here just a little bit. Okay, so here's the building that we're looking at, and what we're going to try and do is determine what's going on with, what's our seismic force that needs to be applied at each floor. Because here's the thing. Everybody in here has had structural analysis, and I know that I taught everybody how to use RISA, right? So remember, you all could say, okay, here's an element, here's a fixed boundary condition, and you could model this frame pretty easily in RISA, but what you need are loads. You need forces in order to do the analysis. So that's what we're going to try and determine right here. So first off, let's do some pretty basic computations. All right, what is the total weight of this building? Say it again. 800 kips. That's a good question. For the purposes of this problem, we'll say yes. We'll just sort of assume this. Depending upon the building, that actually usually ends up not being that big of a deal. I mean, think about it like this. That column, let's say it's a W10 by 49. That's 49 pounds per foot. Look at that. I mean, now let me say this. That's not always the case, and in some structures, like that can be pretty heavy. Usually what I would do is account for everything and then just lump it. But it just depends on your structure. Sometimes it matters, sometimes it doesn't. But I would say more often than not, I would just count everything. All right, help me out. What was our seismic coefficient? 0.1. So therefore, 0.1. Yeah, 1.0, that would be a lot. So therefore, our total base shear which is V, is going to equal CS times W, which is 80 kips. Okay? Sound good? So here's what I propose is happening. I propose that this earthquake is transmitting 80 kips of shear to the building. So the building is seeing sort of an equivalent base shear of 80 kips. So, so the question then is what is that? What is that? What is that? And what is that? So that's what we're trying to determine. Now, one of the things right off the bat when you perform your computation is you are distributing this 80 kips to each story. So a really simple way of checking your math is that when you add up each of these forces, they need to add up to be 80 kips. Okay? So that's just something to keep in mind. Now, next thing, help me out. Are we considering that this structure will contain a braced frame? It's a moment frame, right? So remember, we are considering a moment frame. So because we are considering a moment frame, so we'll say moment frame, does anybody remember what the CT is and what the X value is for moment frames? And this is 0.8. So again, that just changes depending upon what type of system that you're looking at. If you have a moment frame, there's your quantities. If you have a brace frame, there's your quantities. All right. And then, okay, so there's that. Now, HN is the only other quantity that we need, and that's basically the total height of the building, the total structural height. And so what is that? 53 feet. So therefore, what we can do is we can say our approximate period of vibration is that CT value times HN to the X. And so again, that's an approximate equation. Again, to determine the period of vibration, again, is a very complex calculation, and this is making it very easy for us. I just really think that bears repeating. So 0.028 times 53 feet, and that is raised to 0.8. And I know some of you units folks are like, how does this generate an answer in seconds? Just trust me, it does. It's one of those empirical expressions like square root of FC prime. Like it just works, you know. No, that's a good question. Heights need to be in feet. Need to be in feet. There are different constants if you're going with metric and meters. So what's this come out to be? 0.671 seconds. So this structure is going to undergo, every time it vibrates, that period of vibration is 0.671 seconds. Okay. Now I'm going to go back to the slideshow real quick. Let's see. Here's our method of distribution. So we need the weight of each story, the story height. That's pretty easy. But we do need this term K. This term K is a distribution coefficient. So what is our distribution coefficient going to be for this problem? Say it again. 1. And why is that? Because our period is less than 1 second, right? So I propose, so again, therefore, K is 1.0. And if you want a reasoning, you can say TA is less than 1.0 seconds. All right. Are there any questions on this? Okay. Yes.
With
That's a good question, and the answer is no. When we determine, that's a great question. When we determine effective seismic weights, we are looking at, for the most part, self-weights. So, but, great question. All right. Sound good? Okay. All right. The way I like to do this is I like to break this up in a table. So, let's see. Oh, that went down a little further than I wanted. Okay, so the first thing I will list is the level. Okay, and I tend to work from the top down, so because I like to see it sort of as I'm looking at it. So I actually put the roof first, then the fourth story, the third story, and the second story. Oh, I can do better than that. Okay, now the first thing that we're going to list is the weight of each story. So let's see, that's 50, that is 200, that is 300, and that is 250. Okay? And so, of course, you can sum that up and get 800. Okay. The next thing that we're going to list is the height of each story in feet. Okay? All right. So the roof, so this is going to be very similar to what we did before. Okay? So remember when we did our wind computation, we got that this was Z of 0. This was Z of 12. This was Z of 26. This was Z of 41 feet. And this was Z of 53 feet. Y'all remember that? So it's the same thing here. So this is going to be 53. This is going to be 41. This is going to be 26. This is going to be 12. Okay. All right, sound good? All right, so the next thing I'm going to have you compute, so just so everybody's aware, what we're going off of is this equation right here. In fact, I'm going to see some, if I can copy this. Hey, OneNote's all right. Okay, so this is the equation that we're going off of. So what I'm ultimately going to do is I have the weight of each story and the height of each story. So I'm going to take this times this, but then raised to the k. All right. Now, obviously, we don't have to do anything here because k is 1, but in some instances we might. So this is wx hx raised to the k. And it's just the height raised to the k. Okay, so let's take the first one. So what is this times this raised to the 1? 2650. What is that times that raised to the 1? Okay, the next one, 7,800. Good. And somebody else on the next one. Okay. Now, the next thing I'm going to do, I need somebody else tell me what is the sum of that column. So adding those up, what do I get? $21,650. Sound good? All right. So then the next thing I'm going to compute are these distribution factors. So these CV terms are basically distribution factors. So C sub Vx. And they're really easy to compute. So all I'm going to do is for each story, so here's the formula. So I take a term divided by the sum, a term divided by the sum. So the way that I'm going to compute this one is I take the 2650 divided by the sum. And then this divided by the sum, this divided by the sum, this divided by the sum. So let's say 3 decimal places just so we're all on the same page. So what's the first one going to be? There we go. And I don't need a second because that was in cadence. All right. So somebody else on the next one. All right. Somebody else on the next one. I'm making you do work. 0.360. And then the next one. 0.139. So it's very easy to determine whether or not you did this computation correctly. Just add all these up, and what do you get? Should get 1. Okay. And then the last thing that you do is you just take each of these terms and multiply them by V. So what was V again? Somebody remind me, what's V? 80 kips. That's your total base shear. So that's how you know that when it's all said and done, it's all going to add up to be 80. Because if all these add up to be 1 multiplied by 80, these are all going to add up to be 80. So help me out. Say it again. Oh, goodness. Hold on. 9.76. Next one. Somebody else. 30.32. Next one. 28.8. And then the next one. 11.12. Do I have seconds on these? All right, so just for sake of discussion, add these up. What do we get? Just to make sure our math's right. And keep in mind, we could do this in Excel and it all, like we probably have some rounding and whatnot. 80, okay. So there you go. So what you can do is you can say, all right, that F sub 2, so here's the frame. So for instance, start at the roof, and so here's your frame. That's 9.76 kips. This is 30.32 kips and whatnot. So break out your RISA or whatever analysis program you want to use, plug it in, and there's your seismic forces. What do you think? It's really not that complicated, is it? Pretty simple. Any questions? All right. Now, one thing worth mentioning, let's see. In that Excel sheet that I posted online, once it decides to load. So you remember this, the wind example that I did? Well, here's the seismic example that I did. And I actually have that example done in here. So you can see the calculation's pretty straightforward. I think my values are a little bit different, but that's just because it's taking into account all the rounding associated here. So the rounding might be tracking all the decimals out. I even think the only thing I didn't do, I didn't set up the formula to linearly interpolate your distribution coefficient, but I think that's probably a pretty straightforward computation. Any questions? All right. And again, I really don't have a problem on this first homework assignment if you want to use this template. I don't have a problem with that. Okay. All right. So if you're okay with that, I do want to briefly review. So if you're in concrete design, this is going to, we just talked about this. But if it's been a while since you've had concrete design, this will be a nice little review. So remember, those 2 load events are lateral loads, loads going this way, left and right. As for loads that go up and down, we have 3 primary loads that we consider. That's dead loads, that's live loads, and that's snow loads. So dead loads, that's basically the structure's own self-weight. For the most part, either that, any permanent attachment, anything that's not going anywhere. In other words, dead loads are stationary. Honestly, the unit weight of steel being 490 pounds per cubic foot is a value that you all should burn in the back of your head. That should be a memorized value by the time that you graduate with a civil engineering degree. Also that, and then Young's modulus for steel, the E value for steel being 29,000 KSI. You will have that value burned into the back of your head by the time I'm done with you. So those are two primary quantities we're going to use. The unit weight of reinforced concrete is actually pretty relevant to us as well. I mean, think if you're designing this building, these beams are holding up a concrete slab. So understanding the weight of concrete is pretty important as well. Most loads are usually expressed in terms of a pounds per square foot. So for instance, if we're designing this building, how much does the ceiling weigh? How much does the MEP allowance weigh, the mechanical, electrical, or plumbing allowance? How much does the carpet weigh? How much does the slab weigh? All these different components of load are usually expressed in a pounds per square foot manner. You can usually look these up from a specification like ASCE 7, or you can call the manufacturer. So for instance, if I wanted to know how heavy this carpet is, just call the folks that make the carpet. They're going to know that a lot better, probably even than ASCE 7 because they manufacture it. So those are pretty easy to determine. Live loads are also pretty easy to determine depending upon your type of structure. You do need to perform live load reduction, and we'll talk about that here in a second. But live loads are dependent on the type of structure that you're looking at. So live loads, a term that I like to use is occupancy. They are related to the occupancy of the structure, what the structure is being used for. So basically, if you want to know what live loads are for this room, the live loads are us, the people in this room, the chairs, the tables, what the room is being used for, what its occupancy is. So we are the live load. And so that live load would change whether or not you're looking at an office or a school or a hospital or a hotel or what have you. And so ASCE 7 specifies those out pretty easily. Now, the question, one of the things that gets popped up about live loads is what's the probability that they apply everywhere all the time? So to give you kind of an idea, when I started looking at, when I first started learning this stuff and I see, okay, 50 pounds per square foot, I don't know what that means. Like, what is 50 pounds per square foot? How do I visualize that? Well, 50 pounds per square foot, if you have like a 6 foot by 6 foot region, that's about 12 people in a 6 foot by 6 foot region. What you're seeing there, that's 150 pounds per square foot. Okay, that's about 36 people in that region. That's a lot of people. Okay, I did the math on a room, on like this room, and for this room to be fully loaded with people, it would have to see about 100 people in the room. I know there's a lot of people in here, but there's not 100. We don't have 100 people in this room. I mean, what's the probability that a room like this is going to see 100 people in it all the time? Pretty low, right? See, what the spec does is it reports a lot of upper bound sort of expected maximum loads. But what's the probability that those loads are going to be applied over the entire floor area? Not likely. See, what we can do is we can take the live loads, and this is only true for live loads, but what we can do is we can take the live loads that are presented in these documents and then reduce them for the probability that they're not going to see that load everywhere all the time. This is the fundamental expression for live load reduction. Excuse me. So basically what you're doing is you're taking a live load that comes from a spec, this L sub naught. So the L sub naught is what you look up. So that would be what's the live load for an office or a hospital or a school or what have you. And so you're taking that load and you're reducing it by what's going on in the parentheses, okay? And that will then generate a reduced live load that you can use for design. Now, a couple things about live load reduction. First off, I would love to be able to tell you that you could derive this equation with some calculus and some parameters and solve for x. That isn't the case. Live load reduction is an empirical expression. It comes from going out into the field and actually measuring the live loads in buildings and saying, okay, I've got this data. How can I predict this data with a relatively simple equation? And here's what you get. So I don't want you to think that there's, some, well, we can derive for this and solve for x, because that's just not the case. Now, so that's point one. A couple other points. There are some limits on live load reduction. So for instance, in order to limit live load reduction, your tributary area has to be, I don't want to say somewhat large, but if you have a beam that's only responsible for this much floor area, it's like, don't bother applying live load reduction, just design it for the full load. You also can only apply live load reduction anytime that your live load is less than 100 pounds per square foot. We actually talked about this in concrete design just a little bit ago, but to give you an example, for those of you that aren't in concrete, the live load for libraries is about 150 pounds per square foot, whereas the live loads for classrooms are about 40 pounds per square foot. So why are the live loads for libraries higher? The book stacks, right? But here's the thing, okay? We asked about the classroom. What's the probability that this classroom sees 100 people in it? It's pretty low, right? But what's the probability that a library actually sees 150 pounds per square foot? It's pretty high because those books are there. They're not going anywhere. College students don't read books anymore. That was a joke, not a very funny one. But in all seriousness, the library is actually going to see that load. So anytime that your live load is greater than 100 pounds per square foot, you can't apply live load reduction. You have to take the load as is. Okay, so that's another point worth mentioning. There are some limits. Depending upon the values that you enter in, you can get some really wonky answers. So the code says, I don't care what the equation says. You know, if you have an 80 PSF load and you reduce it to 6, like the equation gives you 6, I don't care what the equation says. You can only be limited to reducing it 50% or to 50% for members supporting one floor or to 40% for members supporting multiple floors. So basically, you can reduce it up to 50% for beams and up to 40% for columns. So just for our purposes. Tributary area, I think for our purposes now, I think everybody should be pretty aware of that. If not, for now, that's basically just the area halfway over to the next adjacent beam. I'm actually playing a little fast and loose with that for the folks that aren't in concrete design, and there's a reason for that. We actually don't talk about beams in here until near the end of the semester, whereas in concrete design, we're going to talk about beams immediately. So for now, it's not really that big of a deal, and it won't become that big of a deal until like April. So I'm just going to sort of play fast and loose with that. And then live load element factors for our purposes, pretty basic lookups, just 2 for beams and 4 for columns. The third primary gravity load that we need to consider is snow. Snow is a pretty easy, straightforward lookup. Still got some time, good. Okay. The only thing about snow is that the code reports snow basically like this. They just print off this super, fine print map. The folks at AT Council have done a phenomenal job of taking this, digitizing it, integrating it with Google Maps. It's the same tool that we used for wind and seismic. It's the same location. It'll report snow loads for you as well. As for determining snow loads on buildings, what ASCE 7 reports and what you get from these snow maps is the snow load on the ground. Quite frankly, I really don't care about the snow load on the ground. If I'm designing a building, I care about the snow load on the roof. So what we have to do is take that ground snow load and compute a roof snow load, and it's a pretty basic expression. It just is a function of the importance category of the structure, which I know we've talked about that in significant detail, as well as the exposure of the structure. We've talked about that in detail, and the thermal coefficients. And for most commercial structure nowadays, you might, well, what about angled roofs? Well, for most commercial steel structures, flat roofs are the most common, so it's usually not a big deal anymore. Okay. I know that was a real quick overview of gravity loads. But does anybody have any questions? Okay. Let's talk about load combos. So one of the things that we don't do in structural engineering anymore is what we used to do is we would take all our loads and just lump them into one big equation and say, oh, there we go. We don't do that anymore. And there's a very specific reason for that. It all goes back to uncertainty. See, let's take dead loads and live loads. I think I'm probably going to be a little bit better at estimating dead loads than I am live loads. I mean, if I wanted to estimate the dead loads associated with this floor system above me, really all I need is a calculator and the plans for the building. Because what I can do is to say, okay, here's this drop ceiling, here's how much it weighs, here's the mechanical, electrical, plumbing, here's how much it weighs, here's the beams, here's the slabs, here's the carpet and all that. And I can estimate that pretty easily. But live loads are a lot less certain. I mean, when we leave this room, there's going to be a whole nother classroom that comes in here, and they're going to have, you know, different weights and different loads, and there's going to be different live loads in this room all day, right? So it stands to reason that if live loads have more uncertainty and you're trying to develop a design philosophy where you're trying to ensure uniform safety, well, the load factors need to be different. The multipliers for live loads need to be different for dead loads. And particularly, more often than not, they need to be higher. Okay? Here's the basic load combinations that we use in steel design and in concrete design. So the two equations that you need to be most familiar with are the top two. And for the most part, I know we spent a lot of time in here talking about wind and seismic, and then we're going to spend the rest of the semester using dead and live. If you worry about it, don't worry. I think you're going to find that that this is going to be pretty straightforward. But I really want to spend a lot of time focusing on that second equation. You know, 1.2 dead plus 1.6 live. Why is the load factor for live higher than the load factor for dead? Well, it's because there is more uncertainty associated with live loads than there is dead loads. So if you're less certain about your live loads and you want to ensure a safe design, bump those live loads up higher, okay? And so that's why we specify these load combinations the way that we do. All right, so usually what most software programs do is they do the analysis for all of these different load events and just compute this in one big spreadsheet and report the maximum. For our purposes, really all we're going to be dealing with for the most part when we get to like tension members and connections and things like that is dead load and live load. So it's going to be pretty straightforward. Yes. That's a good question. So the one that's a little unique is L sub R. It's a live load that is just applied to the roof. Usually you're considering live roof loads either A, during construction, or if for some reason there's personnel or occupancy on the roof, but it's essentially another live load. So that's a good question. It's not really handled drastically differently though. It's all basically the same. Any other questions? It's a good question. What's that? No, you did. The short answer is, one, these tend to be specified a little higher, and two, the cases are different because you're usually looking at that stuff during construction. It's not during finished service, day in, day out operations. It's usually during construction. So I would consider that a regular live load because that's related to its occupancy during day-to-day operations. That's a reasonable question, and I would bump that up higher. There are some horror stories though about folks who've had pools not on the ground floor but on higher floors like in hotels, and the structural engineer didn't account for the water in the pool. So they filled the pool up, and then whoever was staying below, no. That's happened before. So yeah, account for the water. Real quick. We don't have. All right, hold on. Shh. All right, we don't have much time left. I do want to mention just two things. Number one, I know I've thrown a lot of details at you about loads. Ultimately, when we really start diving into steel design, which is going to happen when we start coming back next week, bless you, Ultimately, again, our main goal is that as long as the resistance is bigger than the loads, we are good. The last thing I do want to show you before you leave is this. I have posted this on Blackboard. This is homework number 1. It's a pretty straightforward homework. I've given you a frame and a seismic response coefficient and some general characteristics about the site, and I want you to determine base wind pressures and effective seismic forces at each story. And so there's all that detail there. And then I just want you to exercise that lookup tool a little bit. Tell me what the base wind speed is at Iowa State University and what are some seismic response coefficients at Caltech. So next Friday, I would recommend that you get to work on that. Next Friday, I'll leave some room for Q&A on the homework because it's due the following Monday. That's all I got, guys.